Good morning, students, and welcome to this morning's class. We have just had a class on confidence interval for one population variance. We want to discuss in this class the confidence interval for the ratio of two population variances. So what we have as a topic of discussion this morning is confidence interval construction for the ratio of two population variances. Confidence interval. Confidence interval. Hmm? Or we prefer to write it as, let us say, interval estimation. Interval estimation. Interval estimation. For the ratio of two population variances. This could be sigma squared of x all over sigma squared of y, or we can have sigma squared of what y all over sigma squared of what of x. There are two population variances here. Those two population variances are denoted as sigma squared of x all over sigma squared of what of y. So that's what we mean by ratio. Or you can equally be talking about what sigma squared of y all over sigma squared of x. That is variance of random variable x all over variance of random variable y, or variance of random variable y all over variance of random variable what x. When we want to construct interval for the ratio of two population variances, two key things are involved. Those two key things that are involved here are, number one, the sample variances coming from the samples drawn from the two populations or from the two distributions x and y, and then the f distribution. So we need what we call the two things required when we want to construct this kind of interval is, number one, we need sample variances. Sample variances. And these sample variances are given as what we call our s squared of what of x, and what we call s squared of what y. That is variance of sample coming from the random variable x, and then variance of what? Of sample coming from a random variable what? Y. And we are told that whenever we have, then we now say number two, we have what we call F distributions. F distribution. Remember that when we discussed about one population variance earlier in terms of constructing the interval for it, we say that two things needed there are, one, the sample variance and chi-square distribution. Here we are now saying two things are equally needed here. Two, the sample variances, sigma squared of f and s squared of x and s squared of y, and f distribution. And we are told that when we have something like this, if we have what? That x1, comma, x2, comma, down to what? To x what n. That it follows a normal distribution. It follows a normal distribution with parameters mu of x and sigma squared of what? Of x. We are told that if this is true, that it implies that n minus 1 of s squared of what? Of x all over sigma squared of what? X follows a chi-square distribution of n minus 1 degrees of what? Of freedom. And we are equally told again that if we have x1, comma, x what 2, comma, down to what? To x what n. Or let me now be using, yes, let me using y because I'm talking about random variable y. If I have y1, comma, and I have y what 2, comma, down to what yn, which follows a normal distribution with parameters mu of y, comma, sigma squared of what of y. I am told that our m minus 1 of s squared of what of y all over sigma squared of what of y follows a chi-square distribution with m minus 1 degrees of what of freedom. So our concern here is how down do we integrate what we have here now into estimating the interval for the ratio of the two population variances. Another thing I need to recall for you is that we are told that anytime we have the ratio of two chi-squares with their respective degrees of what of freedom, that it follows F distribution. It follows what? F distribution. Let me show you what we mean by that. That when I have chi-square of m minus 1 degrees of freedom all over what? M minus 1 all over what? M minus 1 divided by chi-squared of n minus 1 divided by what? N minus 1 degrees of freedom. That it follows F distribution. It follows F distribution with m minus 1 comma n minus 1 degrees of what? Of freedom. How are we going to show this? Of course, you know that this chi-square here is what I have here. This place. And this chi-square here is what I have here. So what I'm going to do is, in place of this chi-square m minus 1, which is this, I will write the whole of this. And the whole of this thing means I should write, here is m minus 1 of s what square of what of y. Okay? Here I have all over what? Sigma squared. So I have all over what? Sigma what squared dot. I'm still having m minus 1 here. So I have m minus 1 divided by, I come here. Writing this thing implies writing the whole of this. So I have n minus 1 s squared of what? Of x all. Here is sigma squared of x, sigma squared of what? Of x dot. I'm still having my n minus 1 here. So I have n minus 1. I am told that this thing follows a chi-square distribution with m minus 1, n minus 1 degrees of freedom. Of course, I have m minus 1 and m minus 1 here, and then they can go. This will cancel this. I have n minus 1 here and n minus 1 here, so this will cancel this. And if they cancel this, what I have now left is, please permit me to clean the up so that we can show the proof down. So permit me to clean here. So what we now have here becomes that our here, look at what I have here. Now what we have here becomes that s squared of y all over sigma squared of what? Of here of y, of what? Y, then divide by, we have what? S squared of what? Of x all over sigma squared of what? Of x follows F distribution with m minus 1, n minus 1 degrees of freedom. So see what we have here now. What we have here now can be written this way. It can be written this way, that what I have here becomes what? It becomes what? Here is s squared of y, s squared of y all over. What I have here is what? S squared of what? Sigma squared of y multiplied by. When I change it to multiplication, this one goes up and this one comes down. So what I have here becomes sigma squared of what? Of x all over sigma squared of what? Of y. Okay? Now, I want to make it this way. Sigma squared of x, which is what I have here, and s squared of x. I have s squared of what? Of x. So which of course can still be written like this. It implies that this thing can be written this way. What I have here becomes that this thing becomes what? We have a sigma squared of x all over. Here is sigma squared of what? Y multiplied by. Here becomes what? S squared of y all over s squared of x. That becomes what I have. Okay? So if you now look at this thing now, I have now this all over this, and I have this all over this. What are we going to do next? What we are going to do next is simple. We are now discussing F distribution. Let us say that we have interval A and B that are existing at the tails of this F distribution. Let me call those intervals here that I have my A. That my A is given as F of 1 minus alpha over what? 2, m minus 1, n minus 1. And I have another place B. B is going to be F distribution of alpha over 2, degree of freedom of m minus 1, n minus 1. I want to find a situation whereby this A and B will be able to contain this quantity. How do they contain this quantity? And in that case, what I'm going to have becomes, it becomes this way, that my A should be less than or equal to, look at the quantity I have here. So I have sigma squared of x all over sigma squared of y multiplied by s squared of y all over what? S squared of what? Of x is less than or equal to what? B. Now, we are now talking about how are we going to construct this interval with certain degrees of what? Of freedom or level of confidence. This implies that the probability that my A is less than or equal to sigma squared of x all over sigma squared of y multiplied by s squared of what? Y all over s squared of x. S squared of x being less than or equal to B is given to me as 1 minus alpha. That's what we are discussing. So now, I don't have interest in the sample variances. I have interest in the population variances. So I will do everything possible to remove these sample variances from this equation. And removing these sample variances here means I am going to multiply both sides, every part of this equation, using s squared over s squared of x all over s squared of y. So what I have now becomes, I have probability of what? A multiplied by, I am going to have s squared of x all over s squared of what? Of y. Okay? Being less than or equal to, if I come here, it is now going to be sigma squared of x all over sigma squared of what? Of y. Being less than or equal to, I'll come over here, it becomes b multiplied by s squared of x all over s squared of what? Y. This is 1 minus what? Alpha. Okay? So permit me to equally clean. So at this point, of course, our interest, we have arrived at it. What we are now seeing is the ratio of two population variances, sigma squared of x and sigma squared of y. So we are now going to bring out our interval. Let us call that our interval L and U. So I call the interval L and what? U. Where this L is the lower confidence interval and U is the upper confidence interval. So my lower confidence interval here becomes that this thing becomes, here is what we call A multiplied by, we have a s squared of what? Of x all over s squared of what? Y. Being, and then again I have what we call B multiplied by s squared of what? X all over what? S squared of what? Of y. This way is what I have. And of course, we know what our A and our B is. we know what our A and our B is. Look at our A. Our A is given as this. And look at our B is given as this. So putting them into this equation, we have something that looks a bit large. And it was why I decided to make use of A and B. However, at this final stage, let me substitute the value of A and B so I can see how it is going to look. So what I have becomes, I'll open a bracket. In place of this A, I will write the whole of this thing, which is now what we call F of 1 minus what? Alpha over 2 of what? M minus 1, comma, N minus 1. This is for this our A. And of course, I still have my S squared of X. So I have what? S squared of X all over what? S squared of what? Y, comma. When I account for B, I'll write this here. So it becomes what? F of alpha over 2, M minus 1, comma, N minus 1, comma. I'm still left with what? S squared of this. So I now have what we call S squared of what? S squared of X all over S squared of what? Y. I will close the brackets. So what we have here now is what we call the confidence interval for the ratio of two population variances. Sigma squared of X all over sigma squared of what? Of Y. So at any point in time you are told to construct the confidence interval for the ratio of two population variances, just remember this formula. The moment you remember this formula now, you don't have any problem there. This is the last thing we want to show you. Just remember this formula. That this is the formula we are going to use there. And one important thing is that I want to remind you what they say that this quantity is. So permit me to clean this top and show you something. Permit me to clean here. Okay. They told us, of course, if you go through the pages of textbook, they say that our F of 1 minus alpha over 2 of M minus 1, N minus 1 degrees of freedom can be written as that this is equals to 1 all over F of alpha over 2, open a bracket, M minus 1, N minus 1 degrees of freedom. So I can decide to use this in place of this or use this in place of this. If you watch what I have here, this is half over 2. If you watch what I have here, it's half over 2. So it is better to go and read half over 2 and make use of it at the both sides of the equation. And if you agree with me in that, of course, what I'm going to have now as the formula becomes, in place of this, I will now have this. I will have 1 all over F of half over 2 into M minus 1, N minus 1 degree of freedom. Then I have what? S squared of X all over S squared of Y for this one, comma. Coming over here, I'll write what? F alpha over 2 into M minus 1, N minus 1 degrees of freedom. This is the confidence interval also for the ratio of two population variances. So what I'm going to do is to show you how to solve a question there, just one question, in order to manage the size of this video. So permit me to clean here and show you that. That question says, and I write, the question says, let the feeding habits of two species of net casting spiders be studied and tabulated as follows. Let it be studied and tabulated as what? As follows. They call the first spider, net casting spider, to be this. They call it to be this. D-E-I-N-O-P-I-S. That's the name of the first spider. The second one is what we call M-E-N-N-E-U-S. These are perhaps what we call the scientific name or the botanical name of two different species of spiders that cast nets. Okay, they say that the sample taken here, n, is equals to what? 10. And the x bar, which is the mean of the sample here, is 10.26 m. While s squared of what x, which is the variance of the sample coming from this particular species, is 2.51 all raised to power 2. Then under this species, they say m is equals to what? 10, and then our y bar is equals to 9.02 m, while our s squared of what? Y is given as 1.90 raised to power 2. The question here is that we have to construct confidence interval for sigma squared of x all over sigma squared of what? Of y. That's what they want us to do, which is constructing the confidence interval for the ratio of the two population variances of these two species of net casting spiders. So what you are going to do is, once you have this kind of a question, just look at what we have here. What we have here answers everything. And of course, they are looking at constructing 95% confidence interval. 95% confidence interval. And of course, when we talk about 95% confidence interval, it automatically makes this level of significance alpha to be 0.05. So what you are going to have here is 1 all over. 0.05 divided by 2 will give you 0.025. So you have 1 over f of 0.025. You open a bracket. Here is m minus 1, and our m here is 10. So you have 10 minus 1 to be 9, comma. M here is 10. 10 minus 1 is what? 9. So you are looking at f distribution of 0.025 of the two different degrees of freedom, 9 and 9. 9 for the row, 9 for the what? For the column. Then, of course, our s squared of x is given to us to be what? 2.51. So you put here 2.51 all over. Here is given to us to be 1.90. Here it becomes 1.90. Once you evaluate it now, it will give you our our L, which is the lower confidence limit. Then you come here, here is not going to be 1 over. Here it becomes f of 0.025 all over what? 0.05 all over 2, which gives you 0.025. Open a bracket. 10 minus 1, 10 minus 1. It will give you what? 9. And the moment you put it here, of course, I am not going to make a mistake to forget our s squared of what? Of x all over s squared of what? Of y. So once you evaluate this, it will give you the upper and then the lower confidence limit for the ratio of two population variances. Thank you very much for your audience for today's classes. And remember to subscribe, like, and share our videos. Also, remember to stay connected for our subsequent classes. Remember, you are free to drop your worries in the comment section in terms of asking questions where you need clarifications. Once we come across them, we'll definitely come to your rescue. Thank you very much.